our last example of being able to find the zeros of a polynomial function using our rational zeros theorem, we have x to the fourth plus x cubed plus 5x squared minus 17x plus 10. This would be very, very difficult, if not impossible, for us to factor without using the rational zeros theorem. Okay. We notice that p in this case is 10, and we notice that q in this case is the coefficient of x to the fourth, which is 1. Factors of 10 plus minus 1 plus minus 2 plus minus 5 plus minus 10. Factors of 1 plus minus 1. All right, so that makes it easy because all we have is 1. So when we divide this out, our possible rational zeros, so possible rational zeros are just going to be whatever p is, because whenever we divide by positive or negative 1, we just get whatever the numerator is. So plus minus 1, plus minus 2, plus minus 5, plus minus 10. Now, let's go ahead and see which of those is an actual zero. Okay, so for part B, let's start with the low-hanging fruit. Let's try 1. Okay, so that gives us 1 to the fourth plus 1 cubed plus 5 times 1 squared minus 17 times 1 plus 10. And what that means is we're going to have 1 plus 1 plus 5 minus 17 plus 10. This is 7. 7 minus 17 is negative 10. And clearly negative 10 plus 10 is going to be 0. All right, so we just got lucky on the first one that 1 is going to be one of the zeros. Remember, that means two things. X equals 1 is a 0. So right away, that's one of our solutions. But also x minus 1 is a factor. All right. And so now what we can do is we can use polynomial division to be able to try to reduce this polynomial. Or to factor, excuse me. So we have x to the fourth, x cubed, 5x squared, negative 17x, and 10. And so we just go through our synthetic division, drop down the 1. 1 times 1 is 1. 1 times 2 is going to be 2. 1 plus 7 is going to give us 7. And so we get a negative 10. And then finally, 1 times negative 10 is going to give us a negative 10. And that means our remainder is 0. Okay, that's good. And so what that means now is that our function h at x can be written as x minus 1, okay, from our factor up here. And then we just take in order. So we have x cubed plus 2x squared plus 7x minus 10. Okay. And now what we're going to do is, and we haven't seen this before, is we're not going to focus on this anymore. We're done with this for right now because we know that that's a factor. Let's go here and try to find the zeros of the remaining cubic. Okay, so whatever the linear term is, we're done with it. Okay, we're done with linear terms because we know the zeros. So let's try to find a 0. Okay, and remember, we already know the possible rational zeros from up here. So these should still be the possible rational zeros because if we expanded this, we would get back to the original function. Okay, so let's try something like 2. Okay, so h at 2 is going to be 2 cubed, and we're not finding h at 2. Let's just let x equal 2. All right, so let x equal 2, and we're going to substitute it back in just to that part. Okay, so that's going to give us 2 to the third plus 2 times 2 squared plus 7 times 2 minus 10. Looks like it's going to be too big. We get 8 plus 14 minus 10. All right, that works out to be 20, I believe. Clearly not 0. All right, so that's too big. Let's try something a little smaller, okay? Let's try 1 again, all right? And it's okay to have the same factor twice, okay? It might happen. So let's let x equal 1 this time, okay? And so that's going to be 1 to the third plus 2 times 1 squared plus 7 times 1 minus 10, okay? It's going to give us 1 plus 2 plus 7 minus 10. And it looks like that it works. Okay. And so that means that once again, x equals 1 is a 0. So again, x equals 1 is a 0. And also, x minus 1 is a factor. So now what we're going to do is we're just going to synthetically divide just this. Okay, so like I said before, we're done with this x minus 1 for right now. Okay, so if we just plug our 1 in, and remember we had x cubed, 2x squared, 7x minus 10. 1 times 1 is 1. 1 times 3, 3. And then finally, 1 times 10 is 10, and we get a 0. Okay, so what does this mean now? Okay, so remember, x minus 1 was a factor. Okay, we also had another x minus 1 here. So that x cubed minus 2x squared minus plus 7x plus minus 10, our h at x now is going to be x minus 1 from the first x minus 1. We have another x minus 1. Okay, so again, we have two factors of x minus 1. So remember, up here, we had a factor, and over here, we had a factor. Okay, and then we still have this remaining x squared plus 3x plus 10 from the result of our synthetic division. Okay. Now, at this point, we could either try to factor this remaining trinomial, or we can use the quadratic formula. Okay. By the way, another way to write h at x would be x minus 1 squared, x squared plus 3x plus 10. And I want you to notice that this has a multiplicity of 2. Okay, so x equals 1 has a multiplicity of 2. So we need to hold on to that till the very end of the problem. Okay. Now we're going to solve this. I don't think we can factor this nicely. So let's go ahead and use our quadratic formula. So x is going to be -3 plus or minus the square root of 3 squared minus 4 times 1 times 10 divided by 2 times 1. And then if I simplify this, that's going to be -3 plus or minus 9 minus 40 divided by 2, which means that we get -3 plus or minus the square root of -31 divided by 2. And of course, -31, we can't simplify that without using complex number, because we can write that as -1 root times root 31, or I roots of 31. Okay, so two ways to write this part of the solution. So we could write that as -3 plus or minus I roots of 31 divided by 2, or -3 halves plus or minus I root 31 over 2. All right, so those are our other two solutions. All right, and so finally, what that means is that we have our 4 solutions for this. Okay, so let me erase this just so we have some room in here. All right, and I'll write out our 4 solutions, and then we could check that to see what it means on the graph of the function. Right, so our 4 solutions are going to be x equals 1, x equals 1, x equals -3 halves plus I roots of 31 over 2. And then finally, we have x equals -3 halves plus I roots of 31 divided by 2. Now, when we write this, we're only going to write x equals 1 once. And again, it has a multiplicity of 2. Okay, so those are our 4 solutions. Now, a couple things to keep in mind, okay? One of which is that, remember, the original function was a 4th degree polynomial, okay? So take a look of all the way at the beginning. And remember, at the very beginning, we had a 4th degree polynomial, okay? So that means that there should be 4 solutions. So n equals 4, which implies 4 solutions. And remember, this has a multiplicity of 2. So this is two solutions. This is one solution. That's two solution or another one solution. So that makes sense. Also, remember we talked about at the very beginning of the section, if a plus bi is a solution, then a minus bi is also a solution. All right, and I think I made an error up here. This should be negative 3/2 minus I roots of 31 over 2. So excuse me. So this is our other solution that we have. Okay, so this is our conjugate pairs. Okay, so that's where we can check to make sure that's okay. So it's a good thing I checked just to make sure that I had the right answer by having our conjugate pairs. Okay, all right, so that's everything that we need to know to be able to solve our polynomial sorts of functions for the zeros, except for one last I guess, rule that we're going to use, and that's going to be Descartes' rule of signs. That's going to tell us how many possible rational or how many zeros that we have, either positive rational, positive or negative rational, or complex solutions.